Okay, welcome everyone to this continuation of what is machine learning in mathematics. So, you know the drill by now. It's part 12. Video itself relatively self-contained, but still it's machine learning in mathematics, not the other way around. And today I would like to talk about a result that I found very surprising actually, because I'm in this naive, and maybe not even naive, but in this belief that certain types of mathematics are just really difficult. Would like to tell you about, well, how AI and symbolic mathematics in a certain sense interact. And I'm going to follow this paper, Deep Learning for Symbolic Mathematics. So they're actually a little bit more precise. They don't say AI, they just say deep learning. And we will have a look at this paper, Deep Learning for Symbolic Mathematics. So neural networks, blah, blah, blah. And essentially the point is the neural networks are really good, or have been proven to be really good for a long time ago for anything statistically, right? A neural network is like an approximation of something, so it can detect statistical patterns, and it's not quite clear how it will do in something like symbolic mathematics. And that's what the paper addresses. It's not the newest paper around. 2019, the field is developing really, really fast. But anyway, it's still, I think they have still really pretty impressive results that I'm going to, well, address in this video. So let's have a look. It's all about integration, right? The symbolic mathematics here is referring to symbolic integration. And what I was talking about before, what I always find very difficult, and I thought was really, really extremely difficult, is integration. So if you learn calculus, then you will learn how to differentiate a function, and that's pretty straightforward. And then the inverse operation, you will guess it's pretty straightforward as well. But turns out that integration is like one of these, that you really don't want to do. It's like really difficult. Just finding the area underneath a function. What I really want to find is, of course, the function f such that f prime is small f, right? So that's the whole point about integration. And yeah, finding this function is usually like really difficult. But note here, as soon as you have f, getting back to small f, so to verify that you have a solution, it's actually pretty easy. Right? So kind of that's part of what we're using in the following. So you can easily make a kind of randomly generate the test set or something, or make a huge test set, because so there are a lot of tables and whatever. So it's kind of easy to generate data. So maybe we can try to see how a neural network does wherever human struggles, as far as I can tell. I don't know anyone who can do integration like very nicely. Turns out AI actually can. It's kind of a very surprising result, as I said. Anyway, if you don't know what integration is, probably this video is not for you. But anyway, it's kind of finding the area underneath the function. And the point is, this is like known to be a very difficult problem. Yeah? It's kind of classical question, very classical. First integration is probably due to the Greeks. So Archimedes or someone. I mean, they haven't written it down in the usual calculus sense. But finding the area of something or the volume of something using some kind of cutting methods of small squares and pasting them together, kind of in a limit of sums, right? It has been around for a long time. And it's actually a really difficult problem. And you can easily see that this is a difficult problem, because one of the easiest shapes in mathematics ever, the ellipse that you get from, for example, a conic section here, it's a very simple shape. Not difficult. If you have a circle, it's even a bit easier. So in special case of an ellipse. But the parameter of an ellipse, which is an integral, you can't actually express that in any nice way. So there is no like x or algebraic polynomial function or something like for the parameters or the circumstance of a circle. So for ellipses, it's really difficult. So you cannot expect, even if that simple example, you cannot solve the corresponding integral in a nice way. So you usually cannot expect nice solutions to integrals. You know? It's kind of what it is. The integration is like horrible. It's very, very difficult. So people developed like many, many, many methods to tackle integration. I said again, kind of very classical question, difficult classical question. People think about it because it's important. Now, if someone really argues whether integration is important, I'm happy to do that happy to discuss it with you, but maybe this video is not quite for you. So I kind of assume that people believe me that integration is somewhat interesting. And there are many computer programs that can do that. So here's some Mathematica code. Very simple code, whatever. Integrate whatever, bloop, and you get something. Integrate whatever, bloop, and you get something. And I really like this example because here you can see kind of a very harmless polynomial divided by some square root of something. Looks very harmless. The numbers here 5, 6, 4. And then you get these ridiculous type of solutions here. Yeah, so integration is like really difficult, right? So even in a computer, it's essentially hopeless most of the time. So just to be clear here, the way I have approached integration for essentially all of my life, and I'm very old, so for all of my life is I use the machine because it's too difficult to do it by hand. But apparently, that's what this paper tells me, I always used the wrong type of machine because I always did, I mean, this is still very useful, obviously. I always did this type, right? So integrate something, use some algorithm behind it. There's Ries's algorithm, for example, and they have all huge limitations. And whether, in this case, Mathematica can really solve it or any other computer algebra system is a bit of a, well, probably not. There is this wannabe theorem, which I have never seen as a really formal theorem written out. But essentially, if you write down a random equation in algebraic expressions, so nothing fancy, right? Something like the standard functions, it's quite very likely that there won't be a nice solution. So this looks to me like a quite a difficult problem. You might want to zoom in on a nicer set where you know that there is at least a nice solution and want to study that set, right? Not the general set. The general set is way too difficult, but maybe some nice set. And even on that nice set, most algorithms will give up eventually. And then those two very brilliantly here came around and said, maybe we just feed that into a neural network and see what comes out. And it's really surprising. One of my favorite results in how neural networks can be applied to mathematics. It was really successful. Yeah, it was, as far as I know, one of the first uses of a transformer in mathematics, and the results are really, really impressive. So like 95% plus. And they compared that, we'll zoom into the paper in a second, with like the standard computer algebra systems. And they usually outperformed them by a lot. It's kind of very surprising. It's kind of very, very effective what they did. They also studied ODE, so differential equations was kind of the same. But let's stay with integration. So they have those, if you scroll down, they explain what they do. It's a very nicely written paper. Have some statistics. Explain how the data is collected, which is very important, of course. And then explain how the data is collected. And then they have the results. And it's like ridiculous what they achieved. So on integration, essentially perfect scores, which is very impressive. In particular, if you compare it with, so they compared it with whatever, Mathematica, MATLAB, Maple, kind of the standard computer algebra systems that can solve integration, and they did way worse on the corresponding data set they used. So like 5,000 test equations is quite a lot. 500 test equations in this case. And essentially they were even faster. So here they say Mathematica was timed out after 30 seconds, and our solution kind of usually gives a solution, or our approach usually gives a solution in less than a second, which is like a very surprising, very effective application of a transformer. And if you ask ChatGPT or something nowadays in 2025, when the video is recorded, to solve an integral equation, it's actually pretty good in doing that. And yeah, so this was one of the first indications that this is actually really true. So very, very good results on something that looks, at least to me, naively, like a really difficult problem, right? So anyway, apparently integration, at least on the tests that they generated, if you want to know the details, of course the paper is linked in the description. On the tests that they generated, integration doesn't seem to be that hard. It's kind of very surprising. And it's not like they had kind of easy things, right? If Mathematica or MATLAB or whatever fails with a certain probability, not trivial probability, it can't be all that much of an easy test that they had. So here's one of the solutions. We can actually do that in the paper again in a second. But essentially it's kind of fun because the neural network is not, I mean, it is an algorithm, but it's more like a statistical algorithm if you want. So if you run that it might generate different solutions. So these are all the same solutions, they're just differently written, and it might be interesting in its own right. So it's a little bit nicer and a little bit bigger here if you scroll down in the paper. So all of these I kind of can believe that this and this one is the same solution, but maybe this and this one looks quite different. But anyway, so they generate different looking solutions. They're all the same, but kind of different expressions for solutions, which is, as far as I know, not really possible in any of the standard algorithms. So if you play with Mathematica or something for a long time, or you have done this, you probably will see from time to time that it generates some more different solutions, which is more a bug in Mathematica than a feature. But here it's actually, maybe I shouldn't have said that, but here it's clearly a feature of the approach, right? So a neural network is more a statistical way of doing this, and it's kind of generates statistically those equations, and it's correct in 90 whatever % of the cases. And as soon as you have the solution, it's kind of easy. You just differentiate and check that it's true. It's kind of a very, 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 very great application of machine learning to mathematics. Anyway, I hope you enjoyed this video, and I also hope to see you next time.